So this will be a good summary of all of the main properties that we have for line integrals. And now let's kind of see this in action for an example. Let's consider that we have the following problem that we want to solve. So suppose that we have a wire, a helical wire, with a mass density along the wire. So this is going to be mass per unit length along the wire. So along the length of the wire, that is quadratically varying with distance from the origin. The question: what is the total mass of the wire? So this is the question that we want to answer. And this is a great example because it kind of takes an idea directly from physics and is giving us a direct example of where this line integral comes up and why it's really important physically to understand our interpretation of the line integral. But by the way, I also want to point out that this example could be word for word replaced with an example from electromagnetism. We are asking for the total charge of the wire. And honestly, wherever else you could come up with an example where you have a density function or some function of something per unit length, right? You could use that as an example here. So it's a very, very important idea. But so first things first, we'll say that phi of r is the mass density, the 1D mass density along the wire. Right, so this is measured in mass per unit length because it's mass per unit length along the wire. So phi of r here is going to be some constant d. This constant d just guarantees that the units will work out correctly, times x squared plus y squared plus z squared. So here I put quadratically varying or quadratically proportional with distance from the origin. So in this case, we know that x squared plus y squared plus z squared is the same thing as the length of r, or distance from the origin, squared. It's the magnitude of this vector. So this gives us exactly what was asked in the question. Specifically, we're asked for a quadratically varying mass density that's quadratically varying with distance from the origin. What is the mass of the helix? So this is our density function for this problem. And then the curve that we want to parameterize here is the helix. And we'll make this simple on ourselves. We'll just consider a helix. We won't consider the rate of rotation. We'll just consider the helix. It is rather general, or general enough for our purposes. The helix with a radius of r and then a growth rate in the z direction of a. You remember that this was the correct way to parameterize the helix. And we'll also say that we just do this over one turn of the helix, or for t from 0 to 2 pi. Because you could go over multiple turns, and we'll see that that's as easy as changing the bounds of integration in our line integral. So we'll just do one turn though, so from 0 to 2 pi. So before we even go through to calculate the integral, we're going to want to go through and remember our nice formula for the line integral of a scalar function. They're going to involve integrating with respect to the parameter t. We're going to need to calculate the magnitude of r prime of t, where r prime of t is the tangent vector to the curve. So let's do that first. And we remember for the helix, it was a relatively nice result that we got. That this is going to be negative r cosine of t, or sine of t. It's the derivative. We r cosine of t, and the third component is just a. And so the magnitude of r prime of t becomes the square root of this squared plus this squared plus this squared. And I'll let you go through the simplification again if you don't remember, but this ends up simplifying to just the square root of r squared plus a squared. It's very nice because this is constant. We also see in this integral, this definite integral, that we have phi of r of t, or the value of this scalar function along the curve, at every point on the curve. So we need to figure out what that is, and this is going to be phi of r of t is d times x of t squared plus y of t squared plus z of t squared, which when we plug in x of t, y of t, and z of t, I'm hoping you can see that exactly r squared cosine squared plus r squared sine squared plus a squared t squared. So phi of r of t is just d times r squared plus a squared times t squared when we go through and simplify this. These are always, when you're evaluating a line integral of a scalar function, the things you want to do before you even go through and do the line integral. Because now, evaluating the line integral over c is easy. And this is exactly, because phi is a mass density function, the total mass is going to be the line integral over c of this mass density function. And so this is the integral from 0 to 2 pi of phi of r of t times the magnitude of r prime of t dt. So the total mass then is going to be equal to the integral from 0 to 2 pi of d times r squared plus a squared t squared times r prime of t magnitude, which just is the constant square root of r squared plus a squared dt. And now this becomes an integral that we can go through and directly evaluate. Right? This simplifies to the mass is equal to d times the square root of r squared plus a squared times the integral from 0 to 2 pi of r squared plus a squared times t squared dt, which is d times the square root of r squared plus a squared times the integral. Well, this antiderivative of this function is going to be r squared is constant, so it's r squared times t plus the antiderivative of t squared, which is going to be t cubed over 3. That's going to be a squared times t cubed over 3 from 2 pi to 0. So the total mass then is equal to d times the square root of r squared plus a squared times r squared times 2 pi plus a squared over 3 times 2 pi cubed. Which we can simplify a little bit to a nice final formula. It'll be d times the square root of r squared plus a squared times, and I'll put 2 pi at the very beginning because it's part of a constant. In factor out of 2 pi here to get 2 pi, so d times 2 pi times this times r squared plus and what's left over when you factor out the 2 pi here is going to be 2 pi squared, so it'll be 4 thirds a squared times pi squared. And this is the formula for the mass of any helix, right, of any radius r, of any growth rate along ZA. This formula will give you the correct mass of the helix with a special density function. It's a density function that varies quadratically with distance from the origin over and you can use this formula over any number of terms that you want. You just have to change the bounds of integration. So if you want to go on, one turn or one full turn and a half, you'd have to go from 0 to 3 pi here, so on and so forth. But the idea here is we can get kind of a nice picture of this if we open up Python and kind of do a quick plot in Python to see this. So if we open up our Python window and run the code, not this code, that's for a little bit later on. This right here is a picture of the helix with, and I'll show you the parameters. It's the helix with the parameters of the curve equal to 1, so a radius of 1, and then an a value of 1 over 2 pi. That's what this is showing right here. And you see that for this case, the mass density starts at the lowest point of the helix. The mass density is 1 kilogram per meter. And then as you move along the helix, the density grows quadratically with distance from the origin. Right? It grows all the way up to a maximum mass density of 2 at the very top of the helix. And it's at intermediate values. The density along the helix is at different values for every single one of these colors right here. All right, so we've just calculated a formula using the line integral to give us the mass of such a helix. So for any values of the parameters, we can go through and calculate that. So for example, if we were to open this up, all right, let's just kind of do this specific example that is plotted for us so we can kind of simplify this. For the example plotted, we have that r, the radius is 1, and a is 1 over 2 pi, and d in the example is just 1, and the units of d are a little bit important. I mentioned earlier that d is just a constant to make the units work out nice. This density function has to have units of kilograms per meters, or kilogram per meter, because it's a 1D mass density along the wire. So therefore, this d right here has to have units of kilograms over meters cubed, because you're multiplying it by the square of a distance. So we'll say it has to be, we'll say units of, for instance, mass, we'll say kilograms per meters cubed. We'll make this work out nicely. And again, if you want to, this is going to be measured in meters, and then A is measured in, it's just a constant. So that has to, this has to be units of distance. So if the parameter, say, is time along the hill, it could be angle as well, but I guess angle is probably better. So we'll use, in this case, A is a rate per angle, because we're using t as an angle, radians. So maybe we should use theta here instead of t, but t works just as well. So A is, a rate, and it's measured in distance per angle. And so this A right here is kind of like maybe meters per radian, and that just describes the growth rate along z with respect to angle. It's kind of like a little lesson in dimensional analysis here, but the idea here is that when we go through and plug these values into this formula, we'll get the exact correct value of the mass. So this is going to be 1 times 2 pi times the square root of 1 squared plus 1 over 2 pi squared times 1 squared plus 4/3 times 1 over 2 pi squared times pi squared. You get a super nice simplification. And this is going to be 2 pi times the square root of 1 plus 1 over 4 pi squared times 1. And you have here 4 over 2 squared is going to be 1. You have pi squared over pi squared, which is also 1. So this is just 1/3. And what we're left with is that the total mass is equal to 8/3 pi times the square root of 1 plus 1 over 4 pi squared. And this is in kilograms. Or it's approximately equal to, when we approximate this, about 8.48 kilograms. And it's important to note that if you go through and actually use the Riemann sums that we talked about earlier to approximate this accumulation, you get something that's very, very close, right? So the Python approximation of this value ends up being about 8.49. So this is from the Riemann sum approximation that we talked about earlier. So the not far off from the exact value, which is really nice. And it also shows that for complicated integrals, sometimes numerical methods are the way to go. Numerical approximations of the integral is definitely the way to go. Well, good. So this is this will be the end of this example right here, and what we want to move into a little bit is the idea of how to investigate a vector field, the behavior of a vector field, with this concept of the line integral. And this is going to be a specific idea. It's right. So using the line integral with a vector field F. And sometimes some sources don't distinguish the line integral of a vector field and the line integral of a scalar field. I think it's really, really important to distinguish between the two, because in some sense, in a very real sense, as we're going to see, the line integral of a vector field is going to be kind of defined using the line integral of a scalar field. So, right, it's important here that we kind of mention that this function phi that we're talking about and we're integrating is a function, just a scalar function from three-dimensional space to R. It's valued in the real numbers. Just want to kind of mention that, and then here we're going to move into defining the line integral of a vector field, right, where F is a vector field. So it's a mapping from three-dimensional space into three-dimensional space. So the question is, how can we do this? And the main idea is to think of, well, suppose we have a direction field, U. Suppose we have a direction vector defined on every the unit direction vector defined on every point of the curve C. And we want to measure the total effect of the vector field on C in the direction of U hat, where U hat of t is a unit vector that points in a specified direction at every point along the curve. So it's important to kind of think in terms of pictures with regards to what's going on here. So we're in 3D, we have some curve, and this curve is immersed in some vector field. It could be a fluid flow field, it could be an electromagnetic field, it could be a number of different vector fields. But what we're saying is that we have some direction vector U hat. The black vectors here are the F at R, and the blue vectors here are some vector u hat, which could change. It could be a different point in a different direction at any given point along this curve. But suppose we want to figure out the total or the net effect of the vector field f on the curve C in the direction of u of t. Well, we know that at one point, at any given point t, the way that we do this is through the projection vector. Right? We do the projection of f of t in the direction of u hat of t, which is equal to the dot product, and it's really just the magnitude of this projection is what we care about. So we recall that the projection vector is the dot product of f, so it's f dot u hat times u hat. Right, this will give you that f dot u hat is just going to be the length of the vector field f cosine theta, where theta is the angle between u hat and f. This gives you whether the projection's positive or negative, and it really just gives you the component of f in the direction of u hat. Remember, f here is a function of t, and u hat is also a function of t. So we kind of stumbled upon inadvertently, right, what we mean by this, the way of getting the total effect of the vector field f on the curve C in the direction of u of t. It's to take the line integral of this projection, right, because we know that the line integral of f, the line integral of phi of s ds over c is the accumulation or net buildup of phi on the curve C, and specifically if we consider the line integral over C of f dot u hat ds, or in terms of our actual bounds, the integral from a to b of the vector field f of r of t dot product with u hat of t times the magnitude of r prime of t dt. All right, this component right here, this is saying take the accumulation of f dot u hat, or the total accumulation or net accumulation of the component of f in the direction of u hat along the curve C. All right, so this is really a measure of just like the net action of a vector field f in the direction of the unit vectors u hat along this curve. Now this is an important idea in its own right, but it becomes very, very special when we consider special values that u hat of t could take. So special directions that we might want to just consider. So we'll consider first, and this is going to be a really, really big idea here. So consider the special direction where u hat of t is the tangent vector to the curve. Remember, the tangent vector of the curve is the derivative of the position vector along the curve over the magnitude of the derivative or in terms of just arc length, is just dr ds. Right, this is one of the things that we showed. So if we consider this special direction, what we actually end up getting is, and this is in many sources just called the line integral. So when a lot of sources talk about the line integral, by default they're talking about this. This is the line integral of a vector field. Now, I just showed you that we can have more complicated, more different types of line integrals of a vector field depending on what u hat is, but many sources call the line integral of a vector field, they just straight up define it as this integral. So it's the accumulator, it's the integral of the line integral over C of the vector field F, depends on R, dotted with T hat on the curve, ds. So it's the line integral of this scalar function. This is sometimes called the line integral of the vector field. And the reason why this is important, and all these notations are important, we'll see in a second, that this is the same thing exactly mathematically, because T hat is drds. A better notation for this, and the notation that's more often used, is the line integral of f of r dot dr, or just f dot dr for short. These are just some common notations for the line integral of the vector field f. And really what this is giving you is it's giving you a measurement of the net accumulation of the vector field f dot t hat, or the net accumulation of the vector field acting tangent to C. You could think of it in kind of like a rotating sense. And the net accumulation or effect of the vector field rotating in the direction of the curve. If this value, right, is positive, right, so if it's positive, that means that in general, right, f generally goes with C. If it's less than 0, then more often than not, f goes against C. And if it's equal to 0, then f goes equally with and against. So that kind of balances out. Direction. So this is a very useful tool, and we're going to see that it's a super useful tool for many different applications. Another very common notation that you'll see for the line integral is it uses the fact that f is typically we denote it as PQR. Right, so this is coming from this notation right here. you could write this as the line integral over c of p dx plus q dy plus c dz, where you remember that dr we'll write as r prime of t dt. Right? But dr is really just the vector. You can think of it as like dx, dy, dz, the differential. So this is another very nice notation, and I guess the last notation that we want to see, and I want to show, and it's really not notation, but it's how you would go about evaluating one of these line integrals. You can evaluate it using either this notation right here or this notation right here. The idea is this is saying that the line integral over c of f dot dr is the same thing as f of the position vector on the curve as a function of the parameter t. And we'll actually use the original formula right here because this is the line integral that we know how to evaluate right now. But all of these notations are equivalent and mean this exact same thing. This is f of r of t dot the unit tangent vector, which is r prime of t divided by the magnitude of r prime of t. Then with respect to ds, which is really just the magnitude of r prime of t dt. And you see what's a magic cancellation here. So we're seeing that to evaluate any line integral, all it takes is to take the integral of f at r of t, and then take the dot product with r prime of t, whatever that is, and just integrate that dot product with respect to t. So in some sense, it's actually a little bit easier to take than the line integral of the general scalar field because it's a very special combination. And it doesn't involve taking the magnitude. All you have to do is take the derivative. But this is the best formula to remember if you want to remember exactly how to get the actual value and compute the value of a given line integral with respect to a vector field. All of these notations that I've drawn down are equivalent to this, right? They mean the exact same thing. But probably the most common that you'll see for a line integral is this notation right here, but this really is coming directly from this idea, the idea of accumulation of the vector field tangent to a given curve, and that's why this right here is the way of evaluating it. Even this notation makes sense, right? If we go through and we have a curve that's parameterized, and you want to view it in terms of this notation right here, which is sometimes easier, right? This dot product is the same thing as the integral from a to b of p of r of t times x prime of t dt plus the integral from a to b of q of r of t times y prime of t dt plus the integral from a to b of r of t of t times z prime of t dt, right? So if sometimes evaluating these three integrals is easier to evaluate than this dot product integral right here, but the point is that this is what you're going through and doing, right? And it's why this notation makes a lot of sense. so we'll see in some examples, right, how to kind of use this, and how one of the most important concepts, right, that we're gonna be able to consider is the concept of you know, what's called being path independent. Right, so this is going to be one of the huge ideas that is going to be very, very important to us. And the reason this is going to be super important for us is because we'll see that path independence is directly sort of related to this idea of a conservative vector field. And most line integrals are path dependent. They depend on what path you take to evaluate them. But we'll see that a very special class of line integrals is path independent. So we'll prove some theorems on that later on. But I guess an important notational point, and this is not just notation, this is actually an important physical quantity. We'll define now what's called the circulation. The circulation of a vector field F around a closed curve C. So this is important. C has to be a closed curve. So we define the circulation of a vector field F around a closed curve C as the following. We say it's the line integral over this closed curve, the circle here, the line integral over C of F dot T hat ds, or in our other notation, the line integral of F dot dr. And with our previous interpretation of this accumulation, it makes a lot of sense why this is called the circulation. It's kind of like this value, if you calculate it, gives you a direct measurement, right, of how much this vector field is rotating with this curve C, or tangent to this curve C. That's exactly what this integral is giving you a measurement of. So this is kind of like a very special idea here, and it's going to lead to some very big things. One of the biggest things that I can say now is that we can actually get using this idea of circulation, we can redefine or get an alternate definition of curl. And we do that in the following way. So suppose we want to define the curl of a vector field at some point r using the idea of circulation. Right? How can we do this? And recall that the following: for a vector field F, the curl of the vector field F was defined relative to an axis n. Right? The way that we use this is we say that this, the curl of the vector field F, in the direction of n is the amount that F is rotating around the axis n, and this is definitely going to be measured at the point r. Right, so that's important to specify here that we're evaluating this at the point r. This is at the point r. And the way that we can do this in terms of the circulation is actually in terms of a limit. And And it's a very intuitive idea, but it has very, very kind of deep connotations and deep, reasons for working. So we say that the curl, and I'll avoid using the vector language. I said we don't want to. It is in fact equal to the curl or the cross product of that del operator with the vector field, but I want to avoid the way that we defined it earlier. So we'll just use the word curl, which I think is a nicer way in general anyway of writing down the curl of the vector field. So if this is an alternative definition, we can say that the curl of the vector field f in the direction of n hat is going to be defined as the limit as delta A goes to 0 of the circulation of the vector field around delta C of f dot dr of the circulation of the vector field around delta C divided by delta A. It's the limit as this delta A goes to 0. So what is this exactly telling us? Well, it's saying the following. It's saying that if n is some direction, and the contour C is some contour, or the contour delta C is some contour that is progressively getting smaller and smaller and smaller, this is say delta C1, delta C2, delta C3, where the corresponding areas are getting smaller and smaller and smaller as well. At the limit of the in some sense the average circulation over the area delta A, this limit as delta A goes to 0 is the total curl, amount of curl at that point, right? The amount of rotation at that point. In this case, and this is right here the point R. So up here in this limit, delta C is a contour or a curve centered at R. Going around N. And A, or delta A, is the area of the surface bounded by delta C. So this is one way of, or a different way of defining the curl. And what's really nice here is that in some sense we can think of this for small values of delta A as like a measure of the average circulation of the vector field F on the curve delta C. And we're going to see that this definition of curl is perhaps actually better than the previous definition of curl, and more importantly, it's exactly equivalent to our previous differential definition of curl as long as f is smooth enough. So this is perhaps a better definition for curl. And not only that, but it's exactly equivalent to the previous definition. And one of the reasons that it's so useful is it's a useful approximation tool. So for instance, for a small enough curve, so for a small enough curve, delta C, delta A also has to be small as well. We have here that the curl of the vector field F dot n at the point R is just approximately equal to, because that limits, the limit is delta A and delta C go to 0, but if they're small enough, then this value, the curl of F at a point, is going to be approximately equal to the circulation integral over delta C of F dot dr divided by delta A. Which means that for small enough delta A and delta C, the circulation around a curve is approximately equal to the curl at some point times the area of delta A, where delta A is the surface bounded by delta C. So this is a useful approximation very often if you want to, say, approximate a circulation, and will definitely be useful in your homework and the web work.